Good afternoon, all. So, in today's class, we are going to go over review. So, these slides, if you have noticed, you have gone through this before. So, maybe you might have seen this in your math classes or discrete math. So, some of these are kind of you already know. But we are going to do this because we are going to use this specifically this knowledge to create or to find out time complexity. So all the summation series or the series that we are going to discuss here, we will use to calculate algorithmic complexity or time analysis. So that's why we are going to review it in today's class. So some of the things you might find it that you already know it, but just to remember that you need to know it also for this class. Now, another thing is all the series that we are going to discuss, you don't really have to memorize because when we solve multiple let's time complexity examples, you will realize that how we are using it. So eventually you will memorize it automatically. So you don't have to memorize as such, but you will know that after solving 10 or maybe 10 problems, solving time complexity, you will realize that you already know this kind of knowledge. Now, this is prerequisite material. We will going to encounter this, and again, those will be different chapters in different books. So, whichever textbook you are following, you have to. I think in one textbook it is chapter 1, and another it is chapter 4. So, algorithmic complexity, or they will have some reviews. And in one book, I think it is also named as review. So, you figure out depending upon the topics which book and which chapter and that falls that covers. So the mathematical review is about the exponents, how we use exponents or some basic formulas regarding logarithm, then different series, so summation series, or you might have seen series like 1 square plus 2 square up to n square, then some recursive definitions, proofs. So proofs are not really, we will come across it as we need, but basic definitions of series we are going to see. So this very basic formula, something raised to 0 is always 1. So that something might be any integer number. So here we are specifically looking for, or maybe we will consider positive integer number. So here, let's say x is any positive integer number, then x raised to 0 is always going to be 1. Now that x might be 2, so 2 raised to 0 is 1. It can be 3, 3 raised to 0 is 1. If you have x raised to some degree a multiplied by, so here nothing is given, you assume this is the product, multiplied by x raised to some b, then when we calculate the exponent, we are going to add it. So for example, I have given you here 2 raised to 1 multiplied by 2 raised to 2 will give you 2 raised to 3. So this is 2 raised to 1 is 2, 2 raised to 4, 2 raised to 3 is 4. So this is nothing but 8, this is nothing but 2 raised to. So exponents, and when the base is same, then only we are going to add. Now if there is a division of x raised to a divided by x raised to b, then eventually we are going to have negation. So whatever is at numerator, the exponent, minus whatever is the exponent of denominator, x raised to a minus b. So here if we have 2 raised to 3 divided by 2 raised to 2, we are going to use 2 raised to 3 minus 2. So basic maths formula is equal to 2. Now here is another thing, whenever we say something raised to minus n, so 2 raised to minus 3, we convert it as 1 divided by 2 raised to 8, is 1 divided by 8. So 1 divided by x raised to 9. But if you have both, the base is same, but now instead of here x raised to b, if we have exponent of this whole term, so something like 2 raised to 2 for the whole bracket raised to b. Now here we are going to multiply these both exponents. So we are going to say 2 raised to 2 multiplied by 2 raised to 6. So for example, if we are going to say 2 raised to 2, 2 raised to 2 is 4, raised to 3. Here also you will see that 2 raised to 6 is. Now another common mistake is when we are doing it in terms of addition. So x raised to n plus x raised to n. So that is not x raised to 2n. So that is always the base. Since it is addition, it is x raised to n happening twice. So that is equal to 2 multiplied by x raised to n, and it is not x raised to 2. Another thing is if we let's say replace the x by 2 raised to n plus 2 raised to n, that is nothing but so 2 raised to n plus 2 raised to n equal to twice 2 raised to n. So that is nothing but 2 raised to n plus 1. So very simple formula, also very simple rules regarding exponent. Now we will also see some rules regarding logarithm. So whenever we say something raised to 0 is equal to 1, if we want to convert it into log, anything based, so log based anything 1 is equal to 0. That's why we are getting x raised to 0 is 1. Anything raised to 0 is 1. In other words, so if I take log of both sides, what I get is the log of x raised to 0 is equal to log of 1. So here, if you take logarithms from both sides, you are getting 0 log of 1. So irrespective of what base we are taking, the log of 1 is always. Now, if we are taking, let's say, log of x, so base x and sum b is equal to a. So in other words, that is nothing but. So for example, when I say log base 264 is, what is the answer? 6. So how this 6 is coming? Because log of is 2 raised to 6. So this number 64 is nothing but 2 raised to 6. So when we solve it, we get the value 6. So similarly, log to the base 2a is equal to 3 because 2 raised to 3 is. Now another thing in this class, you might have studied in previous that whenever previous classes that whenever we say log, then generally we assume that the base is 10. Right? But in this class, whenever we are saying log, we always assume that the base is 2. So all the algorithms typically when we are calculating time complexity, generally it is big. So for example, when we are talking about binary search, we are dividing the problems. So if we say the time complexity of binary search is log n, then it is always base 2. So unless otherwise specified, whenever you see log some number, let's say log n, then you always assume that this is log base 2. So log is base 2. So that is general assumption. Then if you say log in this way, then that is used for base 10 or base 10. Then when we say ln, then we are going to assume that the base is e, natural number which 2.7. So unless it is specified, always when we say log something, we are assuming that it is base 2. And then we are going to assuming that the base. So log A is So whenever you say log, it is base 2, LG is base 10, and then is base 2. Now some rules regarding logarithm. So whenever we have log to the base a, ab, it is nothing but log to the base a plus. So we are going to simplify this as log a plus log b. Whenever a and b are greater than 0. So they have given one example. If we are calculating log base 10, 3 multiplied by 4, we can simplify it as log of 3 plus log of 4. And if you calculate this value, then you will realize that it is the same value as if we calculate log 1. So that this value and this value matches. So this we might use it in some of the calculations. Then another similar thing is if we have negation or if we have division of logarithms. Similar rule is for negation. So anything, if we have log 4 divided by 3, we can simplify it as log 4 minus log 3. And if we calculate either log of this term or if we do negation, we are going to get the same. Now, similarly, if we are saying log base a raised to n, then that again we can simplify. So suppose we have log base 2 and we have to calculate 2 raised to 10. Then in other words, we can also say 10 log of 2. So this is nothing but, so whatever is the, so this is another way of simplifying. Now you can see that the base here and here is same. So we get the value as same. Then again, we saw division. So here, if you want to change the base, so if you want to change the base from, let's say 10 to 2, or if we have some value, or we have to calculate log of 5 base 10, then we can also do that log. We can change it as log of 5 divided by log of 10. So we are changing the. Then here, when we are saying this value, again, when there is no base given, for all of this, the base is 2. So log of 10, 1024 is 10 because this is nothing but 2 raised to 10. So we know that 2 raised to 10 is 1024. And also 2 raised to 20 is this value. So when we simplify, if we say log of, so here also it is log base 2, here also it is log base 2. So here the note, in our textbook log is always 3. Now here are some summation series. So you might have seen. So we are not really proving this series or anything, but you might have seen this as part of proofs. Typically, when we saw the induction proofs, you might have seen these proofs. So let me write those summations. So we had 1 plus 2 plus 3 plus up to some n. So if you remember, it was n plus 1 divided by 2. Now, how are we going to use this in terms of calculating time complexity? Now, you will see that there are some loops where every time it will print. So let's say first time the loop prints once. Second times it prints something twice. Third time it prints something thrice. Fourth time it prints something 4 times. So if we calculate the number of times it is going to print some value, then that will look like the number of times it is printing will look like a summation series, that 1 plus 2 plus 3 plus 4 plus up to n. And then we have to calculate what is the time complexity of this. So if you calculate this is the number of times something is going to get printed. So if you solve this, so you will get something n square plus n divided by 2. So you will realize that if there is one loop which goes in incrementing order, in sequential order, although it looks like linear, actually it gives me the number of times in terms of n square. So if there is any loop which runs in this manner, then we know that the time complexity is in terms of n square, or this is a quadratic time complexity. So we are going to come, or we are going to solve a lot of problems regarding time complexity, but this, the summation series for 1 to n, or 1 square to n square, or 1 cube to n cube might be typically useful if you want to find out the time complexity. At least you should know that this leads to something in terms of n square. So this is the basic formula we all have seen in the induction proofs. So n plus 1 divided by 2. Now I will not go through the proof of induction, assuming that you have already seen this. If you think we should go, maybe we should quickly go one of the classes. But I assume that you have seen the proof of induction, why the left hand side is equal to right hand side. Then similarly, if we go to the 1 square, 2 square, and 3 square up to n square, if you look at the time complexity or the number of times it is going to print something, then I believe it is n plus 1, 2n plus 1 divided by 6. Then similarly, we also had 1 cube, 2 cube, 3 cube, up to n cube. And that will also be some equation in terms of, let's say, n raised to, I think it's square. So this type of series we might want to do. Now, sometimes it might happen that this might not be straightforward, and it might not be one. It might be in terms of, let's say, some number n. So if you look at this series, this particular series, which goes 2 raised to 0, 2 raised to 1, 2 raised to 3, or that might happen at any a. So the first time group prints a times, then it prints a square times, then a cube times. So if we generate this type of a series, which goes like a raised to 0, a raised to 1, a raised to 2, up to a raised to n, then what will be the total number of times it will print the loop? So the standard formula is a raised to, I think, n minus 1 divided by a raised to no, a minus. So again, this a might take any value. So if we some formulas might happen that first time it is running once, then second time twice, then 4 times. So it is a growing exponential at every iteration. So that is also pretty much a possibility when we are running some kind of formula. So if we have this formula handy, it becomes very easy to find out the time complexity. So if you observe that there are some loops which are running in this particular manner, and we have to find out, then we know that we have this formula for series, that a raised to n minus 1 divided by a minus 1. Now here we are going to substitute a as 2, and then we are going to say 2 raised to n minus 1 divided by 2 minus 1. So the denominator term is really not necessary. So these are typical formulas we might need by calculating. So sum of first n integers. So this is another way of saying the same thing, that when we are adding or when we are looking at the summation series, we are adding number I. So when we are saying 1 plus 2 plus 3 up to n, the another way of saying the same is by using the summation symbol, summation of some integer number I which starts from 1 and which goes up to n. So those many times I'm going to add I, where the value of I increments from 1 up to n. So this is the same thing we can also denote with the summation sign. And here we are going to write I. So every time it will go from 1 up to n. So it will eventually be giving us the same equation, and that is nothing but n plus 1. Another thing is in books, they might have used capital N. So in some books it is small n, in some books it is capital N. Small n is more common, so I will mostly use small n, but you can use anything whichever you are interested. So while giving formula or giving complexity, you can as well write O raised O of n or O of n, where n is input size. So both are correct. So in this case, I'm just giving you an example. So this gives us something in terms of n square we saw, and then how we convert it back or how we get rid of this, that we will study in the next presentation. And now sometimes you will realize that the for loop is not exactly running into the summation series. So it might not always give you 1, 2, 3 and similar in that fashion, but it might give you a series which has a pattern. So for example, if you look at this series 2 plus 5 plus 8, and that series goes up to a number which is something multiplied by 3 minus 1. So if you notice, all these numbers 2, 5, 8 are 1 negated from a multiple of 3. So if we have series in this way, for which we do not have a direct formula, but for which we can use the formula that we already have. So sometimes we might have to use two formulas that we already know, and the combination of both will give us a series. So that is also a possibility. So if you look at this and notice how the numbers are growing, you will realize that it is nothing but if I write something like 3 plus 6 plus 9 plus 12 up to some number. So all these numbers are 3 multiplied by 1, 3 multiplied by 2, 3. So it is going up to some k. So instead of n, they have used k here. Going up to some k, or in other words, we can say 3k, because it is multiplication of a number, multiple of 3. Minus, every time we are going to negate 1. So my first number I am getting if I negate 1 from 3. Second number I am getting if I negate 1 from 6. Third number I am getting if I negate 1 from 9, and so on. So my last number will be 3k minus 1. Now, if you look at this series, so eventually what I'm going to do is I'm going to take 3 common. So if I take 3 common, inside I'm going to take 1 plus 2 plus 3. So this is my known series which go from 1 up to k, minus, and that numbers, whatever is k, those many times I'm going to negate 1. So this number is nothing but k, I'm going to minus. So this combination will give me the time complexity, or the total number of times, or the number which gives me the series 2 plus 5 plus 8 up to 3k minus 1. So the very first inside bracket 1 to k will give me my obvious answer, k plus 1 divided by 2. This is my known series. This series we are multiplying by 3, and then after multiplying by 3, we are going to minus k. So now I know that even though this is not a known series, sometimes just by observing patterns, we can try to fit in, or we can try to fit that into well-known series, and then that might be useful for calculating the time complexity. So is this example clear? You might use it in some of your examples. So why, how we converted this unknown series into the well-known series? So 3 multiplied by the summation series minus from every number we are going to minus 1. So total number of times we are going to do that is k times. And if we are going up to k times, then the number will be 1, 2, up to k. And then we are multiplying it by 3 to get the first number 3 minus 1. Now again, sometimes it might not be possible to fit into series. So we have to then, in that case, we will see some different approaches. So not every time it is a ready-made series that we will see. Now another thing you might come across specifically when we are not in terms of time complexity, but maybe when we are typically when we are learning about hash maps, we'll come across this a lot. So this operation is called as modulo congruent operation. So it is nothing but a remainder operation. So when we do division, we know that there is a division and remainder. So when we perform mod 10 operation on these numbers 81, 61, and 1, so we are taking the remainder. So if we divide 81 by 10, the division is 8, and 1 is the remainder. So generally, all our operations, we care much about division, but this congruent modulo operation, so A is congruent to B modulo N. It means under modulo N operation, A and B are equivalent. So if we talk about 81, the remainder is 1. So if we look at the modulo operation, 81, this is how remainder operation is given. Modulo 10 by the percentage sign on your keyboard. So our remainder is 1. So when I say 81 divided by 10, my division is 8. But when we say 81 remainder 10, this is the remainder. Now when we have this remainder, again if we do, or if we divide 61 by 10, then also I get the same remainder. If we divide 1 by 10, then also we get the same remainder. So under mod 10 operation, I can say that 81 is equivalent. So it is not equal to, because the numerical value is not same. But 81 is equivalent to 61, because if I do modulo operation on both of them give me value 1. The same thing with 1. So if I again take 1 modulo 10, I still get the remainder as 1. So under this modulo operation, I can see that these p values are equal. Okay. Now there are some more equalities in this case. One equality is that if A and B are equal, or are A congruent to B under modulo function, then if I multiply something to A and if I multiply something to B, then the values I receive, that will also hold the congruent modulo function. So in other words, if I multiply 81, let's say by 2, I multiply 61 by 2, I multiply 1 by 2. So the values I'm getting here, I might get 162. Here the value might be 122. Here it is 2. Then under modulo function, these are also equal under the same modulo function. So if I take 162 modulo 10, I'm also going to get 2. If I get 122 modulo 2, I am also going to get value 2. If if I get 2 or if I find 2 modulo 10, that value is also going to be 2. So if A and B are equal, then if I multiplied by some D, both A and B, then the values of AD and BD are still congruent modulo or still equal under this congruent modulo. Similarly, if I add a common number C to both A and B, so for example, if let's say that number is 6, and for 81 we are adding 6, so we get 87. 87 modulo 10, we get 7. If the same number I added to B, 61 plus 6, we get 67. And if again we calculate remainder, we get the same number. So if we add any C to A and to B, then under this function, they still both will have same number. So A plus C will be equal to B plus C under congruent. So either you can multiply or you can add, you will still get the same order. Another thing here is if we are saying that A and B mod n gives you 0, so when the mod operation gives you 0 or when the remainder operation gives you 0, what does that mean? So if I say here is n and here is AD and my remainder is 0, so the division is not given. Remainder is 0 means AB and here I am getting 0. So when you get 0 as a remainder, it means n divides A and B. Now if n is a prime number, then it means n either divides A or n either divides B. So it has to be true. Either it has to divide A or it has to divide B. Otherwise, it will not be, AB will not be divisible by n being a prime. That is another rule. So again, more so we will use those in hash map and hash function, because we have to find, if we can find a hash function where we are using something remainder of n, where n is a prime number, then also that is a good approach to fit the values in the hash function. So we might come back to this part. Now, regarding a little bit about the recursive functions. So whenever we are using recursive functions, so you might have seen, let's say factorial is a very common recursive function. So if we have to calculate factorial of 5, what we generally do is we call the same function again. So we say 5 and then we call the factorial of 4. Now when we call factorial of 4, it is nothing but 5 multiplied by, so this will 4 multiplied by factorial of 3, and it will keep going unless it reaches to a base. So it has to have a terminating rule. In other words, we also call it a base case. So something similar to the rule of induction. So some base rule we have to have. And when it reaches to that base rule now here, you can have either, so in some implementations, have seen factorial of 0 is equal to 1 is used as a base case, or you can as well use factorial of 1 is equal to 1. So either ways it will work. So if you're saying factorial of 0 is equal to 1, it will run up to the value of this case 0. Or if it is, if you set it up to 1, it will run up to the values. Now, and then you have to define that how recursion will happen. So in this case, since we are going to multiply each number, we are going to have a value as 5 multiplied by 1 less than the original value, and that will calculate the factorial. Maybe if we are doing the Fibonacci series, we will define it a little differently. But then again, the same function will call itself when we are using recursion. So function which is defined in terms of itself is called as a recursive function. So for example, here they have given same function which is factorial and another function which is exponential. Both of these are we can so both of these which we can show in terms of so if we are going to find the exponential, so for example 2 raised to 4, then we can also say that it is nothing but 2 multiplied by 2 raised to 3. So this 2 raised to 3 again can be broken down as 2 multiplied by 2 raised to 2. This 2 multiplied by 2 raised to 1. And this might be 2 multiplied by 2 raised to 0, and our base case might be something raised to 0 is equal to 1. So when it substitutes value, it will substitute 2 raised to 0 is 1, then it will substitute this value as 4, then this value as 8, this value as 16. The another function, so this is our simple exponential function, which we can also implement as a recursive function, and this is a factorial function. So which is if we give f 5 factorial, that should be 5 multiplied by 4 multiplied by 3. And every time I can substitute if I say n factorial, I can say n multiplied by n minus 1. So we are in this case x factorial, x multiplied by x minus 1. So we will see in a minute how the actual execution will appear. So when we are going to break it down, when we have to write a recursive function, again, as mentioned here, there are two conditions. One is we have to, let's say we are writing a factorial function f or maybe fact n. So we will have to have one base case that we are going to define as if n reaches to 0, factorial of 0 is equal to 1, or you might as well have factorial of 1 equal to 2. So either one of these might be your base case, and depending upon that, little bit deeper. And second thing is when it is not base case, then what should happen? So when we are calculating factorial of n, return me n multiplied by factorial of n minus 1. So this is my actual functioning that will happen inside the recursive function. So two things. If it is base case, what should happen? If it is not base case, then what should happen? So if it is any n apart from the base cases, so we don't need to implement both. You can have either one of these. So either one, not both. And then we will return. If it is not 0, then you will return n multiplied by factorial of n minus 1, which is again called the shape function till you reach one of the base cases. So now we'll see the actual implementation. So here they have done, if it is n is equal to 0, they have written n. In another case, they have done it for n is equal to 1. So either case. Now this is your actual function, and the return value is int, because we are going to pass integer values. So whatever the factorial function, that will always return us it. Now, if it is n is equal to 0, it should return 1. Else, meaning it is not the base case, then every time you return me the value n multiplied by and call the same function with a 1 less than given n. So n multiplied by factorial of n minus 1. So this will recursively call. In other words, n factorial is n multiplied by n minus 1. It will use this formula and recursively call. So I think this is the this is another online resource which will also give you some more examples of recursion in Java. So again, assuming that you have used recursion some point earlier. Now, same function we can also do it in this manner that if n is equal to 1, then you can return 1. Else, you do n multiplied by factorial n minus 1. So here it will run one time less than the previous one, because as soon as n becomes 1, it is going to return 1. If you are doing 0, this will run one more time, but the results are same. Now, assuming that we are calling it for, assuming that you are going to call it for factorial 5, we are going to just see how the execution will be. So factorial 5, then it will return 5 multiplied by factorial 4. It will return 4 multiplied by factorial 3, which will return, so the factorial 3 function will return 3 multiplied by factorial 2. It will return 2 multiplied by factorial 1. Now factorial 1, it will encounter the base case because n becomes 1. So the value is already mentioned 1. So it will substitute 1 in case of factorial 1. So factorial 1 will return 1. After that, if you have noticed or seen how the stacks are arranged, so the return values, the calling functions are stored in the stack, and then every time they will reach to that particular source. This will map. This value will be mapped to factorial 1. Then factorial 2, we know 2 multiplied by 1, so it will calculate 2. Factorial 3, it will calculate 3 multiplied by factorial 2 is 6. Then factorial 4, it will calculate 4 multiplied by 6, 24. And factorial 5, it will calculate 5 multiplied by 24, which is 120. So the return addresses are stored on the stack. We come back and then calculate the values. So same thing we can also do with the Fibonacci series. Again here, when the original formula of Fibonacci series is if you have f of n that is given by f of n minus 1 plus f of n. So if for any n we have to calculate, we must know the previous two values. So if I'm calculating it for f of 0, I cannot calculate unless I have given those values. So again here there are two base cases. F of 0 should be given to me, f of 1 should be given to me, then I can start calculating from f of 2 or Fibonacci of 2. So n is 2 in this case. So n minus 1 is 1 and then n minus 2 is 0. So these two values are given to me, should be given to me. So f of 0 is 1, f of 1 is 1. So those are the two base cases. After I substitute those values, I get my first f of 2 value, which is 2. And then I can calculate 3, 4, 5 using two previous numbers, which will generate the series 1, 1, 2. Then next number will be addition of 1 and 2, 3. Next number will be addition of 2 and 3, 5, 8. So here, instead of small, they have used capital F, but again, f of k plus 1 is equal to k plus k minus 1. So this is also another way of saying the next term is addition of present term plus addition of previous term. Meaning, in other words, again, any nth term requires me to know n minus 1 and n minus 2. Now, Fibonacci's numbers also we can calculate using recursion. and the base case will be the two numbers should be provided to me. Progress, how I'm going to make progress? So every time I calculate f of a, next time I'm going to use that value and of a minus 1 to calculate f of a. So that is the this value. Now here we will also encounter the problem if we use recursion there. Of course, this is a good example of recursion. Recursion works in this case. But we'll see that what happens when we use recursion. So this we just saw. So example 1, here we are saying that whenever n grows or whenever the value of n is either 1 or less than 1, then you return 1. So this will return, or this will take care of two base cases. This will also return f of 0 as 1. This will also return f of 1 as 1. For all other cases, it is going to calculate the value of n minus 1 plus n minus 2. It's going to give this addition as now, base case generally kills the necessity of, so whenever you reach the base case of course, you will stop running the recursion. Since at this point, recursion is not needed, will return the value 1. Then after that, for every value of n, it will reduce towards the base case. So when for any value of n, it will reduce it by 1, it will reduce it by 2, and it will calculate the values of these two by calling the function recursive. So if we assume how it works, then in general, the problem with this implementation we will come across soon. So what is happening here is when we are calling Fibonacci 5, it will call in turn f of 4, f of 3. F of 4, we need to know 3 plus 2. F of 3, we need to know 2 plus 1. For 3, again 2 plus 1. For 2, 1 plus 0. For 2, 1 plus 0. Now, when it reaches 1, 0, it will get the base value as 1, 1, 1, 1, 1. So, after that, it will calculate F2 as 2, F3 as 1 plus 2, 3, and so on. But you will see that how many times F2 is calculated? 1, 2, 3. So, these values are going to be repeated. So, although we are calculating F5, we are calling F4, we are calling F3 by recursion, and it is going to call the F2 and F3 again while calculating F5, by calculating F3, and so on. So you will see that these are the problems with recursion when we use it, that it will slow down the algorithm because repetitively it is calculating the same value. So see how many times it is calculating F3 twice, F2, 1, 2, 3, F1, 2, 3, F1, it is reaching to F1, 1, 2, 3, 4 times, F0, 1, 2, 3, 4 times. So we will, now you just remember that not always recursion is the best option. Now, if you look at the earlier examples, exponent and factorial, you will see that there it fits very good. So since the nature of exponent and factorial problem is recursive, you will see that every value is calculated once. So even though we are using recursion, it was quite efficient algorithm. Unlike in Fibonacci, where if we use recursion, we end up recalculating some of the values. So they have shown how when we are calculating Fibonacci 1, we are accessing 1. When we are calculating 2, we are accessing 2 values, and so on. And so many times we are calculating the same one. So that was little discussion before going to the time complexity. Now we will go to the next lecture where we are actually going to learn few things about calculating time complexity. And in general, we are going to discuss how we are going to calculate time complexity. So let me So now this is the lecture 2 I'm going to start, which is about analyzing problems or analyzing time problems. Let's first. So some of the discussion you will realize that we already did some of the discussion in the last class. So that part I'm going to skip. So maybe starting write algorithm and how we can write algorithm. So but that discussion we already had in the last class. So here again another definition of algorithm. It is a step-by-step procedure for solving problem in finite amount of time. So again given more importance to time. If we have some input, it goes through algorithm and it generates some output that we want. So this part we saw last time, so I'm going to skip this. Now this is a very good discussion. Let me understand. So if you assume that I have to find an efficient algorithm. So I have a problem at hand, and maybe there are multiple ways to write the algorithm. So maybe I wrote the algorithm A1, A2, A3. Now I have to find which one of these is a better algorithm. So what should I do ideally? In ideal scenario, again, here we are not going to talk about space complexity. So since memory is available now, we don't it doesn't really matter that if I'm saving 4 MB and instead of that I'm wasting 10 minutes, then we will not go for that. So here we are only going to talk in terms of time. So we want to make the algorithm efficient, meaning that we want to make it to save our time. So if we assume that we have 3 algorithms, how do we calculate the efficient algorithm? So ideally what we should be doing is we should track the behavior of this algorithm. So meaning if my n, if I'm doing, let's say, some algorithm, let's say for sorting, or maybe finding the maximum among the n numbers. So that might be any problem. Now, in order to find the efficiency of algorithm, this is what this is next. So how the algorithm behaves when the input size is increased. So if I have 10 elements now, how much time my algorithm is taking versus if my number of elements increase to 100, how much time that algorithm is taking. So if I have 3 algorithms, let's say A1, A2, A3, and if I have to check the efficiency of algorithms, the first thing I will need to do is to implement all 3 algorithms. Otherwise, there is no way I can check in real time how much time it is taking. So I will implement all the 3 algorithms. Now, next thing, I will change input sizes. So let's say this is my n, which is so here we are going to use n to denote input size. So that is again convention throughout the book. So whenever we are talking about n is the number of elements. So the problem might be summation. In that case, it might be I'm adding 1 to n. If it is sorting, I am sorting n numbers, 1 to n. So everywhere n is the input size. And how that algorithm behaves in terms of time. So some algorithms might be, so maybe let me take down some scale, let's say 10, 20, so it is not to the scale, but I just wanted to show. So maybe this 1,000, maybe but sometime with one. And similarly, in terms of let's say time, this is generally a good unit might be millisecond or microsecond. So let's assume that this is in milliseconds. So after some time, maybe with 100. After some time, maybe with 1000, and so on. So now I'm going to change my input sizes and I'm going to see how A1 behaves. So let's say A1, when the input size is 10, A1 takes 10 milliseconds. When input size is 100, A1 takes 100 milliseconds. When input size is 1000, it takes 1000. When input size is 1 million, it takes 1 million milliseconds. So let's say, so that will be my algorithm is growing, whatever. Now here it is looking different because of the, but generally it will be a linear line, let's say, which will go through all these points. So whatever is my n, it is same as in terms of number. So I can say that in this case, my input size n is proportional to whatever the time t. So it is mapping or it is growing linearly. If n is 10, it is also 10. If n is 100, it is also 100. If n is 1000, it is also 1000. So let's say I have another algorithm A2. When A1 is 10, it takes 100 milliseconds. When A1 is 100, it takes, let's say, 10,000. When A1 is 1000, let's say it takes 1 minute. So you will see that the growth of how the input to the time is in terms of n square. Because now I'm talking about here, my n was 10, so 10, 10. This point is 10, 10. Let's assume that this point is 100, 100, and this point is 1000, 1000. So whatever was my input size, I'm getting exact same as my time. Okay, so something in terms of n, so we can say that it is proportional to the input size. Now here, if you look at the points, if I give my input as 10, I'm getting, or I'm taking 100 minutes. Or if my n, whenever my n becomes 100, it is 10,000. When my n becomes 1000, takes 1 minute. So what is the relation here between n and time? So how is the time increasing? So what is the relation between 10 and 100? 100 and 10,000. 1000 and 1. Is there a relation between these numbers? N square, yes. So when it is n square, it need not be the exact same. Because I'm just giving you to give you an idea. It need not be 100 to 10 to 100, 100 to 10. It need not be exact n square. But I just wanted to show you. It might be 10 to 200, 100 to 20,000. So it might be twice n square. So here in this case, whatever is my n, my time is square to that n. So I can say that here maybe n square is actually proportional to time square of n. Then I might have another algorithm A3 which grows like this, that for 10 the value is something like this. For 100 the value is, let's say, 10. For 1000 the value is something. For 1 million the value is 1000. So now the growth of, let's say, A3, so this is my algorithm A1, this is algorithm A2, this is algorithm A3. And let's say at this point, when my input size is 100, let's say this is 10, when my input size is 1000, so the value is 1 million, let's say, so in this case, you can say that this value of A3 is proportional to log n. Okay, so that is also possible. So which algorithm is better in this case? A1, A2, or A3? How are we going to decide? So that is one thing. How are we going to decide which algorithm is better? So if I have implemented these three algorithms and then I checked it on three different input sizes and we plotted it on graph, then how will we decide which algorithm to use? The one that uses the less time, yes. So in this, which one of these uses the less time? 80. So if you look at very small input sizes, maybe when the value of n is 1, 2, you might not appreciate that the differences are not much. So if you're talking about, let's say, input value 2, if something is growing in terms of n, the value will be 2. Something is growing n square, the value will be 4. Something is growing log n, the value might be 1. So you will see that there is not much difference in these values, typically far smaller values. The differentiating factor will come into play when my n increases. So when n increases to, let's say, 1 million, how much difference will it make? So that's what makes us decide which is the better algorithm. So when we plotted, we saw that A2 has the highest growth rate. Because if you calculate the slope of A2 will have the highest slope because the line's growth rate is very high. A1 has a medium growth rate and A3 has smaller growth rate. So here it goes conversely, meaning that whichever algorithm has less growth rate has a better time or is more efficient. Okay, so it's a it's a reverse kind of a relation. If the growth rate is too high, we don't want to use that algorithm, assuming that it's going to get very worse and worse as the n increases. So we want ideally the algorithm which has a smaller slope or smaller growth. Now again, if we really want to do it this way, it is not really practically possible. One obstruction is that we have to implement all the algorithms. It is too time consuming. Another thing is we have to keep track of using n with different values. Now, another difficulty might be that if I run A1 on a slower machine and if I run A2 on a faster machine, I might get wrong values in terms of milliseconds. So in order to have a fair comparison, I have to execute all the algorithms on the same machine with the same hardware compatibility, and then I can plot something of this type, which is practically impossible. So we are going to take motivation from this approach, but actually we are not going to do it in this manner. We are going to use theoretical approach. So we are not going to implement any algorithm. Whenever a problem is given, we are going to come up with different algorithms, and theoretically we are trying to find out the time complexity of each algorithm and then decide which algorithm we want. So this is just to give you an example how it is expected to do, but again how it is not possible. So it is really impossible to implement all the algorithms and then try it for different input sizes and do it on the same machine. So that's not what we are going to do. So we have to, so this is like experimental studies which are done and which are done in some cases, typically when you have to show that your algorithm is doing better. Typically in research studies, we do it, but not in this class, we are not going to do that. So we implement the algorithm, take different input size. After taking different input sizes, we can use some function like system.current time millis, which will give us time in milliseconds for executing each algorithm. And that will enable us to plot this. So just how I showed you, this is the input size graph versus the algorithm. So again, in this case, A3 is the most efficient algorithm. So this is not. So what are the limitations? Implementing every algorithm will again add a lot of time, which might be difficult. And results might not be indicative if we are not using the same machine. Now, in order to really compare two algorithms and their implementation, we have to have same hardware, software, and same environment, which is also a difficult thing to have. So we are going to theoretical analysis. So we are going to do theoretical analysis in this class. So we are not going to use actual implementation. So the way we studied in the last class, for any problem, we are going to implement algorithm. And then we are going to analyze how many times this algorithm is going to execute. And that number will be in terms of some n. And then we will do that for separate algorithms, and then we will compare which algorithm gives us better growth rate, and that we are going to see. So when we are talking about something which is in terms of n, we don't have to run it for different values of n. Then it also allows us to evaluate the speed without actually running the algorithm. So here, we will go through. This is a very good example. So we are going to start with our starting point is either pseudocode or algorithm. So we are going to use it synonymously. So sometimes if you see that it is pseudocode or algorithms, consider that with both the same. So this we saw last time. It is high-level description of the algorithm that we are going to implement, and it is more structured than English, but is less detailed than program, and is preferred notation, and it hides program design. So it is written in this manner. It is either called as pseudocode or. So let's go through this example. So this is again kind of more structured. We can have a little flexibility and rewrite this algorithm in our own way. And then we are going to calculate. So for this, let's say. So let's say this is a calculation of max. And the number of again inputs I is n. So n is an array given to us for which we are going to find the maximum. So how are we going to find? The way they have done is, so let's say we have array 2, 7, 5, 8, and we have to calculate the maximum number. They're assuming the very first number as maximum number. So a of, again this value will be a of. Right, so we are going to assume that the very first number is my maximum. And then we are going to have a for loop which goes from I is equal to 1 up to I less than n, I plus plus, and for all, we are going to check if I find some a of I which is greater than max, then we are going to exchange the value of max as a of I. And if that doesn't happen, it will not go this way. And finally, we are going to return the value of max. So in this case, initially, if we run it on these 4 numbers, initially our max is equal to 2. Then for these 4 values, we are going to check for this. When it goes to the second, we are going to check if 7 is greater than 2. Yes. Then in that case, my max becomes a of 1. Next time again, I'm going to check is 5 greater than max. So now max is 7. So this condition is not satisfied, so it will not change my max. Next, we'll check for 8. Is 8 greater than the max? Yes. So now we are going to say that the max is 8. and that is our result. So when we have to analyze this, then they are saying that if you are accessing CPU, we are going to assume that every memory access to the memory cells will take unit time. So 1 unit is taken whenever you access that. So here, if we are accessing, let's say, A of 0, we will access and then we will assign it to max. We are going to take 2 memory units. This for loop goes from 1 to n. Sorry, n minus 1. So considering the indices go from 0 to n minus 1. So this will go 1 to n minus 1. So let's say it will go n minus 1 times. And every time we are going to access the value and we are going to check the value. So it is going to happen twice. And at the max, every value might be greater, and then we might end up changing the value, and then in the end, we might return, so that will also exist some value. So if we calculate this, so now these numbers will be little different, let's say, but if you add all the number of operations here, let's say in our algorithm, so 2 twice n minus 1 twice n minus 1. Let's say 2. So if we add all the numbers, I will get something like 4, 6, n minus 1 plus 4. Something in terms of 10 minus 4. Something in terms of 10. So we will come back to this in the next class, and